Now let's consider the time complexity of multiplication. As with addition, we'll assume that any single-digit multiplication takes one step. Also, we'll assume our input size n is the number of digits of one factor, and we'll assume both factors have n digits. Now we could determine the exact number of steps required to multiply two n-digit numbers, but instead let's set up a recurrence relation. Suppose multiplying two n-digit numbers takes t of n steps. How many more steps will be required to multiply two n plus 1-digit numbers? And it's useful to remember, concrete doesn't hurt. Suppose we're multiplying two 2-digit numbers. This will take t of 2 steps and produce a number with up to 4 digits. What if we expanded each factor to a third digit? If p and q are the original 2-digit numbers, our new product can be expressed as, so we'd still need the product pq, which would take t of 2 steps. We'd also need a few more products. 10,000 ab, the product of two 1-digit numbers, because that multiplication by 10,000 really is locating the place of the product. 100 aq, the product of a 1-digit number with a 2-digit number. 100 bp, the product of a 1-digit number with a 2-digit number. Notice that we need to find the product of an n-digit number by a single-digit number. In the worst-case scenario, we'd introduce carry digits, so we'd need n single-digit multiplications and n minus 1 single-digit additions, for a total of 2n minus 1 steps. Now let's consider the problem of summing the partial products. Finding the exact number of additions is complicated because the number of addends depends on the place. But remember, nobody ever complained when a job was completed ahead of schedule. So if we overestimate the number of steps, then the actual number of steps will be less and we'll be fine. Since the partial products of two n plus 1-digit numbers might have as many as 2n plus 2 digits, we can treat each partial product as a 2n plus 2-digit number, possibly with a leading 0. So how many steps will it take to add 4 2n plus 2-digit numbers? So we determined that adding two k-digit numbers took 2k steps. So adding two 2n plus 2-digit numbers will take 4n plus 3 steps. However, it's possible the sum will have 2n plus 3 digits. So when we add the third number, we should assume we're adding two 2n plus 3-digit numbers requiring 4n plus 5 steps. Could our sum have 2n plus 4 digits? No. The sum of three 2n plus 2-digit numbers has at most 2n plus 3 digits. So adding the last sum end will require another 4n plus 5 steps. And so adding the four 2n plus 2-digit numbers will take at most 12n plus 13 steps. And so if it takes tn steps to multiply two n-digit numbers, then it will take steps to multiply two n plus 1-digit numbers. And we'd prefer to express this in terms of n. So we have, let n equal k plus 1, so k is n minus 1, and this gives us, the recurrence relation. Now, since tn minus 1 is a linear function, then we can assume that t of n can be found using a quadratic polynomial. So t of n is big O of n squared, and with some work we can find an explicit formula for t of n. But we're primarily concerned with its complexity category, and so this establishes that it is big O of n squared. But remember, if you want to understand something, solve it again. So suppose c and k satisfy t of k less than or equal to ck squared. Then we can expand, drop the subtracted term, and then we have, now we can do several things at this point. We could change our ansatz. One possibility is to assume that t of n is big O of n cubed, which will work, but since we already know t of n is quadratic, it's unsatisfying. Let's take a closer look at our reasoning. We dropped all the subtracted terms to make the right side larger, but as long as we're subtracting a non-negative amount, we can omit it and retain the inequality. So let's rearrange that. If t of n is less than or equal to cn squared, we can rewrite our recurrence as. So consider this expression, and remember we get to pick c, and if any particular value of c works, so does any larger value. So suppose c is greater than or equal to, I don't know, how about this? And you might be wondering where this expression came from, and perhaps more importantly, how mere mortals can come up with it. And the answer is, remember, the last thing you write is what you've proven. We want this expression to be greater than or equal to 0. So let's start where we want to end up. Remember, the last thing you write is what you've actually proven. Now, as long as we perform reversible algebraic steps, we can work our way backwards. Since we do want to say something about c, let's go ahead and isolate our c terms and shove everything else onto the right-hand side. And everything has a c, so we can factor it out. And as long as k is large enough, 2k minus 1 is positive, so we can multiply or divide without changing the direction of the inequality. And so that gives us our first step. And so suppose c is greater than or equal to this quantity. As long as k is large enough, we can multiply without changing the direction of the inequality, and that leads us to this expression being non-negative. So the inequality holds if we can find c greater than or equal to this for all sufficiently large k. Now, since the limit as k goes to infinity is 8, then for any c greater than 8, we can find a k where the inequality holds, establishing our base step. We still need to find c and k where this is true, but we'll leave that as an exercise. Once we've established our base step, then this term we're subtracting is non-negative, so we can drop it out, and so t of k is also less than or equal to ck squared, establishing our induction step.